Yeah. Okay. Very good. So now we have. Okay. So we were discussing axioms of measurement, I guess, right? So this is measurement. So this is a general case now. Okay, so yeah, what we have a quantum system, the Hilbert space, and Hamiltonian. We don't need even a Hamiltonian. We just need a we just need an observable A from domain of A inside H to H. So this is an observable. Then we know what observables are. These are just self-adjoint, in general, unbounded operators. That's what they are, right? And we saw that definition of self-adjointness involves some technicality that should be distinguished with symmetric operators, which is much easier to check and all that. Okay, so we have one of these things, and then so a spectral theorem for self-adjoint unbounded operator says that there exists a projection valued measure attached to this A. Measure, so we denote it by P, I believe, no, for mu A. So, I mean, this projection valued measure we call PBM, I guess. So they are sort of projection valued analogs of usual measures. So the value of the measure of a Borel set is not a number, it is a projection. So in other words, for all U inside R Borel set, we have this the projection from H to H, and this association satisfies properties that are quite similar to the properties of measures. And the relation between this PDM and A is that A can be reconstructed as basically average value of this observable X, that's the notation. I mean, this is some sort of Lebesgue measure analog of PBM measures. Okay. Now, so this is, so we are given one of these things. So assume also a system is in a state row. Quantum system is in state row. Now, this is state row. These are mixed states in general now because we are discussing the general case. So what is this row then? This row is just a density operator. In other words, is self-adjoint and non-negative operator is trace class, and its trace is equal to 1. These are the general mixed states for any quantum system, at least for closed quantum systems that we are discussing so far. So now to this pair, A and rho, observable is given, and we are going to observe this observable when the system as it is at state rho. And then to this thing, we are going to attach a probability measure on the line. Okay? So to this, we attach a probability measure. I mean, this is really honest to God probability measure. It's real standard probability measure on R. So we denote it by mu A now rho, because it depends on both the observable and the system's state at that moment that we are doing the measure. So what is that? Now I have to define the value of this for any Borel subset of R in order to define this property. And this on U is equal to trace of rho mu A of U. So what we do, this is the projection. We multiply it by this rho, and we take its trace. So this is the value of the, so this is the probability of, so now the interpretation of this number is the following. The probability of having observed a value of this observable in the Borel subset U is this. So this basically is probabilistic interpretation is that this is the probability of measuring the value of A that belongs to U, sorry. I mean, for example, if U is an interval, so the axioms of quantum mechanics is such that we are not going to measure a specific value for A, or fixed value for A. We're going to measure something, and probability of that value to be in this interval is given by this one. That's a generalization of the axiom that we had in the last lecture when instead of mixed state, we had a pure state.
By value of A, you mean mu of A? Or mu of A? Or...
No,
so A is observable, right? So
A is an observable, but quantum mechanically, we don't measure operators.
Right.
For example, it could be position operator, it could be momentum operator, it could be angular momentum operator. So what this says is that the probability of observing the system, its position, for a position of the electron, for example, to be here, is given by this.
Okay.
Yeah.
I see. So yeah, whatever the value of A is that you measure. Right.
We don't know which value we get, but it's a random variable now. Now we have a real honest to God random variable, which are the values of A. And this is the probability distribution of that random variable.
Okay. The values of A are just, what are the values of A? Sorry.
So yeah. So the values of A, given that the system is in a state rho, by the way. The two things have to be given.
Right.
Yeah?
Okay. Yeah.
Is that measure supported on the spectrum of A or something like that?
Yes. Yes. I mean, for example, yeah, that's a good comment. For example, when when A has a discrete spectrum, This is really a sums of Dirac masses, which are supported on the spectrum of.
There's also a continuous parts of the spectrum, but this also accounts for it.
Yeah, this is very general now. Yeah, if there is a continuous spectrum, then it also tells us that we cannot say its probability of being in any value of the continuous spectrum is 0, but the probability of finding in some neighborhood around that point is non-zero. Yeah.
So you kind of restrict it to like a one dimension. Like if you're imagining like, I don't know, position, for example, you imagine position in like a three-dimensional space, but this is, we're talking about for all sets of just R or R to the n.
No. These are on R. So the position operator, each coordinate is a random variable. And we just say what is the probability of having X in that interval, Y in that interval, some other intervals. Yeah.
But I think this is slightly related to what you're asking. You're asking what you're measuring for A. But the point is that this measure is supported on the spectrum of A. So just like you're measuring eigenvalues before, your measure is only non-zero on the spectrum.
Yeah. Oh, so, okay.
Does that make sense?
Yeah, so that's what is the value of A though? I guess that's the one understand.
A value of A. Because when you do measurements, after all, you will find electron in some place. You will measure the spin of electron with some value. You will find its angular momentum has some value, things like that.
Right.
You do really find some real numbers.
Yeah.
You're not, there's no funny business about like operators measured or something.
Right.
These operators and Hilbert space and this thing, these are somehow extra devices that eventually are supposed to give us this.
Okay. Yeah. Okay. That makes more sense. It still bothers me, but I think
yeah, this is kind of indeed, yeah, it's a difficult concept.
Is there like so? Is some value base? There's many values of A that we can observe, right?
Yeah, of course.
Yeah,
it's a random variable.
Right. Just any value of it. Okay. Yeah.
Even A and rho, you construct a random variable or equivalently probability distribution of that random value.
Yes.
Given a measure, a probability measure.
Okay.
So this is the one. So okay, now, so the question is, what is the average value of A when the system is in state rho, right? And this is something that we denote by this notation. This is the average or expectation value A when system in state rho. So we have a probability distribution like this, and we want to compute its average. The average came out, you have to do this integration using this formula. The average came out, comes out to be trace of rho.
What the higher one is.
You can compute using this again.
Is it rho A squared, like the whole thing squared, or is it just A squared? What is X like? Oh, I see. You just replacing this. Okay.
Yeah. So this is this one, and then so this is going to be equal to. So I mean, for example, the second moment is going to be this one. Well, it's not moment. I mean, it's standard deviation variance. So this is equal to going to be trace of rho V2 minus trace of rho A. So that's the fluctuations of this properties. Okay. So this is the thing. Now, it's good to compare this with the situation in statistical mechanics. So, with stat mechanics. So what's the situation there? The situation there is that the configuration space is some manifold M. This is the sort of configurations of a statistical system. And observable in that case is just a function. Say, I'm going to use the word maybe O from M to R. The real values function. And the state of the system, instead of being one particular point on the manifold, is a probability distribution on the system. And rho, the probability measure. It is a probability measure, not just a measure. The probability measure. And then in this case, the average value of O with respect to this state, this probability measure is just equal to integral over M, O of X. And then we have E. And you compare this formula with this formula, you see that this is really analog of that. The integration is replaced by trace. Observable is observable A, and this measure is rho, the density matrix rho. This is what we use in statistical mechanics. Question?
So they have this like we have like can we have like an example of how that works? Like, I don't know how to actually work with an object. I'd like
the simplest case you can take, just take a spectral theorem for finite dimensional spaces.
I mean, like nothing that reduces down to like a sum. Something that is truly a
yeah, I mean, some example of this. I mean, you can take, for example, the position operator and try to find. So, yeah, I mean, so you can take for A to be the position operator, which would be multiplication by X. And then you have to find what is that projection value measure? It's Lebesgue measure in that case. And everything boils down to computing this Lebesgue integrals.
So plug in a number again.
Yeah. Right. So yeah, okay. So in that case, I think we'll get projection onto that interval. You have like L2 function and you're projecting to that interval. But okay, so I don't have a ready-made example, I should say that. So, yeah.
I see this definition of the projecting value measure, but I don't actually know how to work with it. Again, I never really worked with it properly.
Yeah, we can give some examples maybe a little later. That's fine. So now just the last axiom, which is so yeah, I mean each of these topics you can go on and on and on. Obviously, it's a never-ending thing. And I didn't discuss uncertainty principles here, algebraic uncertainty principle, but for now that's okay. I think we should just move on. Yeah. Okay, so that's excellent. So this is going to be, how to call it, statistics or for combined systems. Yeah, so imagine we have two systems, like here is Hilbert space H1 and Hamiltonian H1 for the first system. And then we have Hilbert space H2 and Hamiltonian H2. And then we consider them together. We want to compose a system which consists of this and that. And these are distinguishable. So this is one type of particle, this is another type of particle. They are distinguishable. They are not indistinguishable. So first, this is distinguishable. The combined system then is going to have Hilbert space, which is H1, tensor H2, and this is a not algebraic tensor product. You just take the algebraic tensor product and then you complete it. Because the algebraic tensor product is not complete in general. You complete it, you get a Hilbert space. And this is still I use algebraic notation, but this has to be understood. Okay. So you do that, and then the Hamiltonian is going to be something like H1 tensor 1 plus 1 tensor H2. So this is working on the first leg and identity on the second leg. So this is a system composed of two components. They don't interact and they are indistinguishable. So they are distinguishable and non-interactive. They are non-interactive. If there is an interaction, there is some complicated terms added to that. Right? Okay, so this is the analog of Cartesian product of the configuration space for two classical systems. Now, if they are indistinguishable, and this is something purely quantum mechanical that currently has no classical analog, they are indistinguishable. For example, you have one electron and one electron. Then the Hilbert space of the system depends on what kind of particles we are dealing with. So if they are bosons, there are two cases. They are bosons. We have to take the, so in that case, I'm taking H1, first of all, H1 is equal to H2. Make things simpler for myself. They're indistinguishable. And then in this case, the Hilbert space H, the Hilbert space is going to be S2 of H, which is the second symmetric power of this. So this is going to be equal to symmetric tensors. In H tensor H. But it's a subspace of H tensor H consisting of symmetric tensors. So what do we mean by symmetric tensor? We define a map sigma from H tensor H to itself, or sigma of X tensor Y is equal to Y tensor X. So we can just simply, in this case, define S2 of H to be kernel of 1 minus 6. These are the symmetric tensors. This operator in this case is a nice bounded operator. So this is a closed subspace, and so it's a Hilbert space really, and it gets its inner product, everything from the ambient space, and this is the one. So for bosons, it's this one. So for this indistinguishable, and if there are fermions, so these are bosons. For fermions, we have the Hilbert space is going to be the exterior, second exterior power of H by itself. This one, which is in this case, in fact, is kernel of 1 plus sigma. So it's a kernel of same twisting operator. Okay, so, and you can check that actually these operators send symmetric power to symmetric power and send antisymmetric powers. So the operators, just Hamiltonians, just go through. So now the Hilbert space heavily depends on statistics of these particles, indistinguishable particles we are discussing. In the case of bosons, in the case of fermions. And this continues to systems of n particles as well. Same with n particles. So what do I mean is that in that case, we have like Sn of H. In that case, we have to define appropriate operators here, which we can define. It doesn't matter. You can define it, and you can define the thing, and then with n.
What if you have a mixed system with fermions and bosons? Then you just
So fermions and bosons, they are distinguishable. So we will have a bunch of, I believe, several of them.
We just cancel them off. Yeah,
Something like that.
Yeah, that makes sense.
I mean, we have to work with some examples. So let me give you some examples of this. Question?
What did you say that Hamilton was in this case for the indistinguishable situation?
It's really the same thing because it's defined on the big space, and I'm claiming that sends symmetric to symmetric and antisymmetric to antisymmetric. So then descends to be able to do averaging in this case. I'm not sure, maybe. But, I'm not so fresh on that. Okay, so I mean, when time comes, we can discuss this thing in detail. But I mean, there is this issue. So, but let's look at one example like this. A is equal to L2 of, for example, R, particle on a line. So in this case, if it is, if you have like a boson, you want to have a system of two bosons that are on the line, then we have to look at this H2 of L2 of R for this Hilbert space. Oh, sorry, for bosons, S2. And what is it really? This is just the set of all functions f belonging to L2 of R2 now, two variable functions. That's symmetric. F of xy equal to f of y. So yeah, you have to go through the definitions and make sure that you can do the identification. So it comes out something very tangible. It's really symmetric functions in two variables. And if they are like fermions, we have to take skew-symmetric powers for fermions. H equal to H2 of L2 of R. So that's really like, that's just like, again, the set of all F belonging to L2 of R2. I mean, in this case, f of xy is equal to minus f of yx. Particular f of x and x is equal to 0.
Because of the weighting functions for particle position.
Yeah.
Position x to position y, that they're indistinguishable.
Yeah.
This is kind of demonstrating Pauli exclusion.
Yes. This is exhibiting Pauli exclusion principle. Because these are fermions are by definition also, by some definition. There is a spin definition, but there's also a statistics definition of particles that satisfy Pauli exclusion principle. So this is Pauli exclusion principle. Yeah. Yeah, so that has to be elaborated on because it says that two different particles cannot occupy the same states with the same quantum numbers. Right. That's the way it originally was formulated. But after some thinking, it boils down to this. So there is some jumps involved. So yeah. So these are. I mean, question. Okay, I think now it's a good idea to compare just for once this classical and quantum context, and then see what we have done, and then we just move on with one example of this. Then we'll look at. I mean, there's from here you construct book space. H. So this is the Hilbert space of infinite number of particles. Could be bosons, could be fermions, or could be just distinguishable particles. Depending on that, there are three cases. There is fermionic Fock space, there is bosonic Fock space, so let's call it fermionic Fock space, there is bosonic Fock space, and there is just full Fock space. This one is full Fock space. But I'm not defining what they are, but these are the Hilbert spaces for systems of infinite bosons, infinite fermions, or indistinguishable particles. The one way to do quantum field theory is to work with Fock space. The alternative method is to do path integral. There's two ways to do QFT. So we will discuss. Yeah.
In the Fock space way, is it how rigorous, like is it fully understood the rigorous foundations of it?
Yes.
Oh, okay.
Fock space is completely rigorous. You can define and take sums of all symmetric powers. And there is a completion of that. And you can introduce creation and annihilation operator in the Fock space and start working.
Okay, then why do people still use the non-rigorous foundation package?
Oh, only definition I want.
Oh,
okay. Then
okay.
after that, you have to deal with infinities in this picture as well.
Okay, yeah.
And in fact, conceptually, it's harder to work with this. Only at the beginning, there is some nice feeling. But then after that, it's
okay.
After that, you have to deal with infinities. Yes. Okay, so now the table I wanted to draw this one here is the following. Put everything in context. So we have this like, so we have here classical, and here is quantum. Okay, so what did we have? We had something like, we started with maybe phase space, or configuration, phase space, I would say. State space, let me call it state space. So in classical mechanics, could be, for example, a symplectic manifold. It could be just a symplectic manifold, for example. In quantum mechanics, is the Hilbert space, complex Hilbert space. And you see, they're so different, right? And then states. So these are like, in this case, these are just points of the symplectic manifold. So there is this point. If you are talking about classical mechanics, but if you are talking about classical statistical mechanics, then these are probability distributions or probability distribution, say rho. Here, we can have either pure states, which is corresponds to these x's without mass. Well, pure state is just denoted by something, a point in the projective Hilbert space, the space of lines, one-dimensional complex subspaces. Or we can take density matrix. So, then we can have something like Hamiltonian. Maybe we just discuss observables first. So observables. So in this case, these are just functions from M to R, real valued functions. I mean, we can denote it by F or O. In this case, these are self-adjoint unbounded objects. Bounded self-adjoint. Now, that's for observables. Then Hamiltonian is just a function h from M to R. It's a real valued function on the phase space. It's just Hamiltonian. And in this case, it's also a is a kind of observable, but is a distinguished observable. We pick one observable, we call it Hamiltonian. Usually it has to have some other properties, maybe it's bounded below some nice properties, but in general it's just an observable. H from the mean of So that's what we have over there. And then we discussed also dynamics. We have this dynamics. So the dynamics in this case is Hamilton's equations. I mean, basically, from this H, we construct this vector field, the Hamiltonian vector field XH, and then the flow of the Hamiltonian vector field XH gives us the evolution of the states, pure states in the system. I don't write the equations because this XH, the vector field, defines everything. And anyhow, the equations that are called Hamilton's equations are only in Darboux coordinates. In general, would be very different. In this case, of course, we have Heisenberg equation. We also have Schrödinger equation. We have different equations. So this is dynamics. And so for combined systems, here we just take the Cartesian product of two phase spaces. But here we have to take either tensor product, or we can take symmetric or antisymmetric, etc. And so we can take all of these different cases. Okay, so any questions?
This is obvious to you, but it's kind of interesting to me that how a spectral triple has all the information on the right hand side, but you can recover all the information on the left hand side sometimes. Right, and that's something I've read about.
Yeah.
Although in that case, what are your dynamics for a spectral triple?
Yeah, I mean, we have the Dirac operator. We can look at e to the I T D.
Right. And you could, okay.
That's yeah, that gives us a unitary, one parameter unitary.
Okay. Yeah. And then combining systems also sort of depends on product perspective.
Yeah. It's a bit more involved because of reality conditions and stuff like that. Mm-hmm. So this is a kind of very, very rough sketch of some sort of initiation into quantum mechanics, but there are really, you can talk about these things for months and months and months and months. Always interesting stuff emerges, and there are a lot of things. We can, for example, spend a lot of time looking at cases where this is integrable. You can really solve Schrödinger's equations in closed form. These are already very nice things. You can also spend time doing perturbation theory. That's a huge subject on its own. You can also spend time learning and doing classical quantum correspondence. So there are a lot of things still in quantum mechanics before you start quantum field theory. You can just spend all your life doing quantum mechanics, and still it's very interesting. But that's not what we do. This is just a rough, very rough first sketch of so now what I'm going to do, I'm going to at least do one example, which is the quantum harmonic oscillator. So I'm going to look at this quantum harmonic oscillator, and then yeah. Any questions? So this is yeah, one of the most important examples. Quantum okay, so this is quantization of a system which exists on the line. So we have one oscillator on the line, and when you quantize it, you get the following. If you quantize the Hamiltonian, you get the following Hamiltonian H, which is P2 over 2m plus 1/2, say, Q squared. So now, okay, if we assume that H bar is equal to 1, and if we assume that n is equal to 1 also, these are things. And somehow we have also assumed something about Hooke's constant of the oscillator. The spring constant also we have assumed, I don't know, 1 or something. Frequency of the oscillation, something like that. So if you already, I have done some choices here. If you do that, then you get H equal to P2 over 2 plus 1. Yeah, so let me write it like this: 1/2 E2 plus Q2, which is 1/2 minus D2 dx squared plus x squared. That's this differential operator. Okay, so of course, to solve Schrödinger's equations, you want to solve certain equation. IH bar is psi dt equal to H psi. Again, I'm assuming H bar is 1. Now, one way to solve this equation is to neglect the left-hand side and find the eigenvalues, eigenfunctions, if you can, of the right-hand side. Okay. And so in this case, we are looking for H psi equal to lambda psi. If you do that, then you can solve this thing, because you can take linear combination of these things and then solve the whole problem. So basically, diagonalizing, finding eigenbasis for Hamiltonian is the main thing for now.
pelvic space is also a boundary.
Okay, so yes, I've been too fast here. So A is L2 of R. The space is, yeah, there's no restriction on the particle. It can go anywhere. The oscillator can be anywhere. Okay, so, and if you look at it, this is quite a hard problem because how can you find eigenvalue, eigenfunction of this differential operator? I mean, this is quite hard. So there is a trick that I believe it was first introduced by Dirac. So we're going to write this in terms of two other operators which have indeed physical meaning. And these operators are called creation and annihilation operators. So introduce, and this is a kind of universal feature. So introduce creation and annihilation. Operators. So this is A star and A. A star is creation, annihilation is A. So what are they? They are the following operators. So A is equal to 1 over root 2. Q plus A. A star. You see, Q and P are self-adjoint operators when we do this. When you compute the adjoint of this is of course going to be equal to 1 over root 2 Q minus I. We introduce these two operators, and then of course we have the Heisenberg commutation relations Q and P is equal to IH bar. But H bar is 1, so this is Q and P, commutator of Q and P is I. If you use this relation in combination with A and A star, you notice that actually this gives commutator of A star is equal to 1. So this is one of the nice features that instead of coming out I is really 1, the commutator. You can also write the Hamiltonian H, obviously in terms of these two operators, A and A star. If you multiply them, you're just writing this in terms of product of linear factor and its conjugate, but then there's going to be some leftover. So H, you can check that this is equal to A star A plus 1. This is the questions or so far we have like just reformulated this thing. Now, these operators are called ladder operators also. In fact, you can check the following things. It's not difficult. That if you have an eigenvalue, an eigenfunction, if you apply A, so let's look at imagine you have something like H of psi is equal to lambda psi. Imagine you have found one eigenvalue and one eigenfunction. If you can check that if you apply A to this, H of A of psi is equal to lambda minus 1 A of psi. In other words, if A of psi is not 0, then you are creating an eigenvalue, an eigenfunction with eigenvalue 1 less. You're going down. Okay? And you can repeat. You can go down, down, down by applying A iteratively. You can also check that if you apply a star on the other hand, then you are going to increase your eigenvalue by 1. There is star psi. So this is the crucial observation that that's what I've done. Now compare this. So we also have this relation H equal to A star A plus 1/2. And we are trying to look at find eigenvalues and eigenfunctions of H. If you look at this relation, this immediately implies that this is always, of course, bigger than or equal to 1/2. This is obvious from this relation. So this shows that the smallest possible eigenvalue, the ground state energy, is always bigger, is bigger than or equal to 1/2. So ground state energy. Maybe we denote it by E0. So this is definitely bigger than or equal to 1/2. Now, let us show that actually the ground state energy is 1/2, but by exhibiting a function that satisfies this equation for 1/2. If you look at it here, in order for this to be 1/2, A star A has to be 0 and psi has to be 0. And for that, this is if and only if A of psi is equal to 0. Okay? So in other words, what I'm saying, H of psi equal to 1/2 psi if and only if A of psi is equal to 0. This we can argue from this. So see if we can solve A of psi equal to 0, but A is this one. So this means we have got 1/√2. Q is X, right? What was P? P was 1/IH dDx. H is, I'm assuming, is 1 cancels, so this is plus dDx. Very good. So this is now a differential equation, first order differential equation that you can easily solve. The solution is, of course, psi of x is equal to c e to the minus 1/2 x squared. You can easily solve this. Okay. Okay, so that's it. So you have found the ground state and is unique. The ground state is unique, is given by Gaussian. So C, you can fix it in such a way that the total integral is 1. There's a constant C. So this is now psi 0. When E0 equal to 1/2.
If the other side, you just apply A or A star.
A star, not A. If you apply A, you're going to get 0.
Oh, yeah.
Well, I mean, we designed this to be 0.
Exactly. Okay.
So creation operators create the argument from now on.
We have to go up because
we want to go up. Okay, so the next one, so this is like psi 0. So the next one is psi 1 of x. We apply this A star to psi 0 of x. And now we have to maybe normalize it here. So I call this C0 and then here is C1. So there is some normalization. That's okay. by this general thing, this is an eigenfunction with eigenvalue 1/2 plus 1. So E1 is equal to 1/2 plus 1. And in fact, its picture is like this. I mean, the real points of this is like this. This is style 1. E1 is equal to 1/2 plus 1. It's essentially nothing but some linear function times e to the minus first order. I mean, just x times e to the minus 1/2 x squared, some normalization constant. Now, you can also show that when you apply a or a star, the new wave functions you get is orthogonal to the previous one. So this is already orthogonal to this one. That's also straightforward from it. So yeah, psi 1, psi 0 is 0. So all you have to care about is orthonormality. Orthogonality is done. Okay. And then we can keep going. So then we define psi 2 of x. It's going to be C2, some normalization, a star squared of psi 0. This is as energy E2 equal to 1/2 plus 2. And in fact, looks like, I believe, something like this. These are not up to scales. I mean, they are just a general feature is that. Yeah. Okay, so you can construct infinite number of eigenfunctions and you can find infinite number of eigenvalues. So what are they now?
Are the eigenfunctions just the any polynomials times the exponential? Is that?
It turns out, yeah, it turns out it's that. So, but okay, so but what I'm saying is that so you get this psi n of x, n from 0 up to infinity, and then En, the energy of this state is 1/2 is n plus half. And this is orthonormal basis. Oh, it's orthonormal set. It's not, we don't know if it is a basis or not. That's the crucial thing. Now, what is this? Indeed, as you said, psi n of x is, again, essentially some function hn of x times e to the minus 1/2 x. That's clear. What is hn? Hn is a polynomial of degree n. They are called Hermite polynomials. The exact form is known. There's a closed formula for them, but we don't want to know it right now. It's just all we care is that it's a degree n polynomial, which is Hermite polynomial. So far, with this amazing idea of introducing creation and annihilation operators, we found infinite number of levels. But now, the big question is, did we find all of them? Is that it? So the question now is that it? And in other words, are there any other eigenvalues, eigenfunctions? Is there any continuous point in the spectrum, for example? All these questions. lurking or standing, and we have to address them. So, yeah, this is like half. This is half plus 1. These are the levels. And in fact, they grow like harmonic modes of harmonic oscillators in this sign. Okay, now we can answer this question completely if we show that actually this is an orthonormal basis for L2. So, and that's what we can prove. So let me give you the proof. So, here, this is sign of X is orthonormal basis of L2 of 1. It's an orthonormal basis of L2. Now, okay, so this is by itself is quite interesting because we know that L2 of R is a separable Hilbert space. This we can prove easily more or less. So it has like orthonormal basis of the form E1, E2. We can label them, but showing a particular concrete example of this orthonormal basis is not very easy. This space is not compact. Although it's a Hilbert space is separable as countable basis, but the space is not compact. So you typically, for non-compact spaces, finding orthonormal basis for the L2 functions is difficult. And the fact that we have some very explicit completely known basis like this is really incredible. I want you to think about it. What other Hilbert spaces you know, infinite dimensional Hilbert spaces you know, that you can tell me what their bases are explicitly? Do you know any other Hilbert space with a complete basis? No, compact. I'm just giving you the simple, the easier question. Yeah. Or equivalently, you can look at L2 of silicon. And in that case, e to the I n theta, trigonometric basis is e to the I n theta, and from minus infinity to infinity is an L2 basis, orthonormal basis, yeah. Right? And you can look at tori. There are similar formulas for higher dimensional tori. This basically is the question of Fourier series on compact groups. But on non-compact spaces, finding any instance of such things is kind of difficult. Right now, if you ask me, show me another basis, I really cannot show you another basis. I know there are these bases that people study in wavelet theory. They have amazing properties. They are explicit, but they're kind of very hard to define. Yeah.
I don't know. Just waiting to see how you do it.
Yeah.
And then I have next couple ideas, but I want to see it.
Okay. Okay. Maybe I cannot prove it, and then
No, not like that. Like, it kind of how you prove it. I think I can come up with more bases, but I don't know.
Oh, is that right? Okay.
From RMT, they
oh, explicit. Okay. Well, yeah. I mean, there is, of course, an idea that if you take any set that spans this, sets of polynomials, something like that, and then you do Gram-Schmidt, you're going to get an orthonormal basis, but it's not concrete. Those examples are not concrete. I mean, so we'll discuss it now. So let me give you the proof. So to prove this, we have to show that if you have a function that's orthogonal to all of them, then that function is zero. Need to show, I mean, actually it suffices to show, let me put it this way. F inner product psi n equal to 0 for all n implies that F is equal to. That's what we have to show. Huh? Okay, what does this F inner product psi n means? 0. This is integral over R F Hn of x exponential of -1/2 x squared dx. Right? We know that this is equal to 0 for all n. Now, from here, I conclude that actually, from here it follows that integral over R F x n e to the -1/2 x squared dx is equal to 0 for all n given. So why is that so? Well, Hn has degree n, right? It starts with xn, and Hn minus 1 has degree n minus 1. So you can subtract them, basically, and you can show that the space generated by all these Hns from degree 0 to n is the same as the space generated by 0, 1 to 0, x, I mean, by 1, x, x2 up to xn. We can just, with linear combinations, we can go from one basis to the other basis. We can produce these things. Okay, so once you do that, then you get this. Okay, now we can use Fourier series, not Fourier series, Fourier integral. So in the following form, in what form? I mean, we can just say that. So now let's look at the Fourier integral of f e to the -1/2 x squared. The Fourier transform of this. What is the Fourier transform of this function? This is equal to integral over R f of x, for c, say, is equal to f of x e to the -1/2 x squared e to the I x c, e to the I x c, and then we have got dx, right? This is the Fourier transform of this function. Now, I want to show that this is actually equal to 0 for all c. So what's the idea? Well, what is this e to the I x c? This is essentially sums of these things times Cn. So you can multiply these things by Cn. I mean, e to the I x c is sum of I x c with Rn over n factorial n from 0. You can multiply these things by Cn and then sum them, and then you approximate this function by sums up to some finite level. You see that it's 0. I mean, this goes to 0. I mean, you have to cite the right theorem, which I forgot what the dominated convergence theorem. I'm not sure what the right theorem is, but this is straightforward at this stage. That's the idea. Okay, so this shows that the Fourier transform of this guy is 0. But the Fourier transform is a unitary operator. So it means that this is itself zero. So of course, this is implies that this function is question.
We use the fact that it's a Gaussian energy point besides just a symmetric function, a positive symmetric function.
Sure.
So with the Gaussian term, do we use that at any point besides the fact that it's positive and symmetric?
No, we didn't use it at all. I mean, we didn't even use the symmetry of this.
So if
we just computed the Fourier transform of f times e, and this is non-zero.
Right, and then then you can swap that, and all the moments would be, or all the would be zero because
of this thing.
Yeah.
You have to multiply this by c to the power n, which you can.
Yeah.
And then sum them. So you get the first k terms of the exponential of e to the x is zero, and this converges.
Oh, okay. And I wonder if you had some other, like, let's say you construct an inner product with some nice positive function, like the Gaussian, and you find some orthonormal basis in terms of polynomials in front of that function. Then wouldn't that also everything follow?
The things that come from random matrix theory, they are for weighted Hilbert spaces.
Yeah, so they won't actually span the whole.
They are for weighted Hilbert spaces, and again, they are not explicit.
Some of them are, but like some of the orthogonal polynomials, like if you had a x to the 4 term there, you can get explicit h's.
X to the, what do you mean by x to the 4?
Like minus 1/2 x squared, say minus 1/4 x to the 4.
In terms of Bessel functions or what? In terms of
I think you can get it in terms of like a more like in terms of the combinations of Fermi polynomials.
I like to see that, but they are very rare.
Yeah, they're very rare. I'm trying to come up with another example.
They are quite rare, and
they're very special.
Yeah, I think wavelet theory gave the best answer to the question.
Oh, okay.
Because they not only they are, I mean, they have some amazing properties also, some other amazing properties also, which I won't recall now, but that needs some. That's it. That's the end of the proof. So basically, what it means that we have completely solved the harmonic oscillator in this case. You know all the eigenfunctions and all the eigenvalues. You have really decomposed L2 of R in terms of this basis. And you have diagonalized this Hamiltonian in this basis. So that's the kind of prototype calculation. Ideal sort of calculation. Thing, so to speak. I mean, yeah, I think it would be nice to solve the hydrogen atom. Would be nice to solve also harmonic oscillators in Rn, coupled harmonic oscillators, and it'd be nice to think. But okay, that's time for everything. Question?
I'm not sure. Going back to the circle case.
Okay, so maybe then I will just stop the recording. Okay, yeah. Okay, so I think.